Rainwater Harvesting presented by Contech Engineered Solutions. Before we start today's presentation, we would like to cover a few housekeeping matters that will ensure we have a smooth presentation. We have placed all phones on mute to cut down on background noise and to ensure everyone can hear the presentation. At the conclusion of today's webinar, we will provide information on how to obtain PDH certificates for today's presentation. The webinar is scheduled to last for 1 hour. We have about 50 minutes of presentation followed by a question and answer period. When you logged into the webinar, the Go to Webinar window will have appeared on the upper right-hand corner of your screen. This window will minimize by itself after a few seconds so it does not interfere with you viewing the webinar. If you would like to maximize this window, just click on the small red arrow and the window will be maximized. The blue box in the Go to Webinar window will allow you to minimize or maximize the presentation, so you can view it in whatever size works best for you. If you have questions, please type their questions into the question box. We will be taking them throughout the webinar. Presenting today will be Mark Lelong, Dave Adams, and Catherine Thomason from Contech, and Matt Ray from OptiRTC. Mark is the Rainwater Harvesting Product Manager for Contech and a member of the American Rainwater Catchment Systems Association. Mark has 7 years experience in the stormwater industry and 17 years experience in the water treatment industry. Dave is a senior design engineer with Contech and specializes in rainwater harvesting systems, stormwater treatment, and detention design. Dave has 11 years of engineering experience in stormwater design. Catherine is also a senior design engineer with Contech and currently specializes in rainwater harvesting, stormwater treatment, and detention design. She is an active member of the American Rainwater Catchment System Association and has 9 years of engineering experience in stormwater design. Our guest speaker today is Matt Ray. He is a water resources engineer with nearly 10 years of experience in the environmental consulting field that focuses his practice on project and financial management of projects with complex permitting and compliance issues. Now I would like to turn it over to Mark.
Great, thank you, Lisa. And thank you all for joining us for today's rainwater harvesting webinar. Our topic today is the added cost of reuse is not what you think. So in this presentation, we will review the components of a rainwater harvesting system. Then we will examine 3 commercial site project examples and look at stormwater management design without rainwater harvesting and with rainwater harvesting, and then look at a cost comparison of these examples. Lastly, Matt Ray with OptiRTC will introduce predictive modeling software and explain how it can be used for rainwater harvesting. For those of you who are unfamiliar with Contech, Contech provides engineered solutions for the civil engineering community. Contech's portfolio includes drainage, bridges and structures, roadway and earth stabilization, and stormwater products, which includes rainwater harvesting, the topic of today's discussion. So more and more stormwater regulations across the country are moving to include low-impact development, or LID requirements. This graphic represents the thought process that most LID rules follow. So you can see at the top that most rules favor runoff reduction practices such as infiltration and bioretention. Then the rules allow for flow-through type treatment if runoff reduction is not feasible. So in these situations where runoff reduction is required, rainwater harvesting is a design option that can help achieve runoff reduction when infiltration and bioretention are not options. We will consider this selection process and our project examples as we examine integrating rainwater harvesting into site design where LID practices are not practical. There are several benefits realized by implementing rainwater harvesting. Each of these benefits will hold a different value to the project depending on the situation. For certain projects, the lead points gained by using rainwater harvesting might be enough to go from a LEED silver to a LEED gold classification. For another project, rainwater harvesting might present a design option to increase the leasable space in a building by storing water underground, thereby increasing the value of the project. So in our project examples, we will demonstrate how to view rainwater harvesting as an incremental cost to stormwater management site design in order to evaluate the cost-benefit relationship for rainwater harvesting. So first, let's take a look at the rainwater harvesting system itself. Every rainwater harvesting system for commercial scale development should include the following components: pretreatment, a cistern, and a mechanical system. Now there are a variety of different options within each of these categories to optimize the system to meet the needs of a specific project. And Contech offers complete turnkey systems that include all of the components that you see here. So first, let's take a look at pretreatment. So the purpose of pretreatment is to keep solids, debris, and organic material out of the cistern, which is going to improve water quality and also reduce maintenance costs. Now, some pretreatment devices operate by diverting the first flush, which is going to contain the heaviest pollutant load. And while effective, this method wastes water, and it could result in diverting the entire runoff for smaller rain events. The Contech system, we use a CDS unit, which is a hydrodynamic separator for pretreatment. The CDS unit treats 100% of the flow so that all of the stormwater is treated and collected in the cistern and that no water is wasted. The unit consists of a stainless steel screen and internals housed in a concrete manhole structure, which can be installed in parking lots or roadways, making it a very effective and very versatile pretreatment device. With underground storage of rainwater, one of the things to consider is the size of the cistern and the availability of water for reuse. Now the common thought here is that a cistern is going to be watertight, it does not leak, and we'll size that cistern to hold the amount of water that's needed for the reuse application. However, this might not always be the most cost-effective approach. There's a price to pay for a cistern with zero leakage. So the design should always consider the question, will a slow leak be okay when we optimize the design? So we'll look into this when evaluating the predictive modeling software later in the presentation. Steel reinforced polyethylene, or SRPE, is the material of choice for cisterns for the Contech rainwater harvesting system, which offers the highest level of watertight integrity. Most other types of cisterns, like fiberglass for instance, are limited in size as to what can fit on a truck. So with SRPE cisterns, they're typically shipped in sections, and then the joints are fused right there at the job site. So the configuration of the system is very versatile, and the cistern can be designed and installed in as long a length as needed to accommodate the required storage volume. The SRPE cisterns are offered in diameters from 48-inch up to 120 inches in diameter. And so with this, the SRPE cisterns offer an opportunity to store a lot of water in a very small footprint. So next, we'll talk about the mechanical system. This is how we're going to get water out of the cistern and get it to the reuse application. All of these systems are going to include a pump and at least basic screening or filtration to protect the downstream fixtures. The design and the configuration of this mechanical system is going to vary greatly based on the requirements of the reuse application. So for irrigation, the system is relatively simple with manual flush filters and low flow and pressure requirements. Other applications such as cooling tower makeup or toilet flushing will require a finer level of filtration, and many will include automatic back flush filters. Many building codes will also require some type of disinfection for certain applications. In these cases, ultraviolet or chlorine dosing can also be added to the mechanical system. Almost all of these mechanical systems will also switch over to municipal water as a backup water source if the cistern is empty or if there's a problem or maintenance needs to be performed on the mechanical system. All of the Contech rainwater harvesting systems are hydraulically tested at the factory for flow rate, pressure, and control programming so that we ensure that the system is going to operate as designed when it arrives on the job site. So now that we've reviewed the basics of our rainwater harvesting system components, I'm going to turn it over to Catherine Thomason to take a poll of the audience, and we'll also take time to address any questions that might have come up before we move on to our project examples.
Great, thanks, Mark. Let's take a poll question now. The first poll question is, what is the most valuable benefit of rainwater harvesting? So if you want to select an answer, is that water savings for you? Is that lead points, runoff reduction, or sustainability? So take a minute now and pick what you think is the most valuable benefit of rainwater harvesting. We'll give everyone a few seconds here to vote. Okay, let's look at the results. So it looks like the majority of our viewers believe runoff reduction to be the most valuable benefit with 53%, followed by sustainability, water savings, and then lead points. So thanks for taking that poll question. And we did actually receive a few questions from the audience, so we'll take those now. Mark, can other pretreatment systems be used instead of just the CDS unit upstream?
Yeah, certainly. We can accommodate any type of pretreatment on a rainwater harvesting system provided by Contech. So we've used a number of different devices in the past.
Yeah, and depending on where the water is coming from, filtration may even be a better pretreatment system. So we can use a system like the storm filter. We have a lot of other, Contech has a whole portfolio of treatment systems that might be able to be used as well. One other question that we received, how does the steel reinforced polyethylene tank compare to a fiberglass tank?
Well, it's one of the biggest differences, as I mentioned, is the fact that we're virtually unlimited in the size and the length of a tank that we can provide, because we do the field welding of any sections or joints in the field. So we're not limited to the truck. Cost competitive-wise, it's a very competitive option to fiberglass, and typically a little bit heavier than fiberglass as well.
Great, thanks. Well, now we're going to move on and look at an example site. So in this example, we have a 3-acre site. 1 acre is roof, 1 acre is hardscape, and 1 acre is landscape area. And we're going to assume that this is a commercial property requiring both water quality and water quantity control. So over the course of this webinar, we're actually going to look at 3 examples using these basic project parameters, but with different site assumptions. So in this first example, let's assume that there's only space and infiltration available for the parking and landscaped area, but the roof needs to be treated in a different way. And in this example, let's look at treating that with flow-through planters. So you can see in the sketch, we have 2 scenarios. On the left, the roof is being treated using a 2,500 square foot flow-through planter right next to the building. And then on the right, we're treating that roof runoff with pretreatment and sending it to a cistern so we can then use it for irrigation. So here's a few pictures kind of showing what that might look like on a site. In the upper portion, you can see some flow-through planters right adjacent to the building. And on the bottom portion, you can see what would be required if we were taking that roof runoff and instead sending it into a rainwater harvesting system. First, we're going to pre-treat it, send it to our 31,500 gallon cistern, and then send it through the pump and mechanical skid to use for irrigation. So for these 2 scenarios, let's look at the costs. On the left, we assumed $15 per square foot of planter area times our 2,500 square foot planter for a cost of $38,000. And that $15 per square foot of planter is based on just our prior project experience, but it could definitely vary depending on where your site is located. On the right, we're going to break down the rainwater harvesting system and estimate a material cost of $82,000 and a total installed cost of $109,000. So the difference here between using planters for the rooftop versus rainwater harvesting is at roughly $71,000. So why would we spend that additional $71,000 for rainwater harvesting? Let's look first at water savings. If we were only using that water for irrigation, we could save up to 400,000 gallons per year, which equates to roughly $1,200 a year in water savings. If we upgraded our mechanical system, added some disinfection, a little bit higher end system so that we could also use that water for toilet flushing, we increased the water savings to 700,000 gallons a year, with about $6,500 in savings per year for that alone. Without the planters next to the building, you could also add available leaf space. And so by adding that space, that 2,500 square foot, now of rental space instead of planters, at $21 per square foot, that's a savings of $52,500 per year. In addition, up to 12 lead points are available for rainwater harvesting. So let's look at another example using that same 3-acre site, but with some different site characteristics. Let's assume that we have the space for a pond, very little infiltration on site, and that breaking the treatment into smaller LID basins is not possible. So in this sketch, you can see that we are taking all of the sites, the rooftop, the landscape area, and the hardscape, and sending that entirely to a pond that's roughly 14,000 cubic feet. So what if we took that same example, but we added rainwater harvesting to treat just the roof area? This would decrease our pond sizing and potentially free up some additional parking space. We also are able to meet our low-impact development and runoff reduction goals. So now we've taken that pond and decreased it to about 9,800 cubic feet of storage. In order to determine our cistern size, we used Contech's rainwater harvesting runoff reduction calculator. This allows us to analyze various supply and demand scenarios to optimize that cistern size. This is a free tool and can be found on our website. You go to contechES.com and click on the Design Toolbox header. You'll see some of our various BYO Design Your Own Project tools, one of which is the rainwater harvesting tool. And by inputting just a few details about your project, you can analyze your site, look at runoff reduction, and water savings goals. So as we discussed, we reduced that pond size by about 30%, and we're still using rainwater harvesting for kind of the second scenario, treating just the roof runoff. So the same type of scenario that we had in example 1, storing that water in a 31,500 gallon cistern and using it then for irrigation. We use the Water Environment Research Foundation's tool to estimate the pond cost. Using this model, we're estimating our pond to cost around $30,000. This accounts for both the material and installation of the pond. So on the left, you can see that $30,000, which is discussed with the pond cost. And then on the right, you see we have a pond that is 30% smaller, plus we've added in that rainwater harvesting system. So that's the similar system that we had in example 1. So the difference in cost between these two scenarios is $100,000. So again, we ask the question, why then would a developer pay $100,000 extra to add rainwater harvesting to their site? So the water savings values have not changed from our last example. We still have the same size cistern and are just collecting the roof runoff. But by making that pond smaller, we gain 16 additional parking spaces, which in turn could potentially add to our rental space. By using $21 per square foot of rental space, this could add up to $224,000 a year in potential income for the site. Plus, you still have the lead points as an added benefit. And I'm going to turn it over now to Dave Adams to walk through example 3.
Thanks, Catherine. Example 3, we're going to look at the stormwater management for the site using underground detention. The assumptions going into this example are that the site has poor infiltration rates and that there's limited space for an above-ground pond. So the underground detention and treatment would be ideal for this type of site. The graphic shows all of the drainage from the site, the surface drainage, the green space, and also the rooftop runoff coming to a pretreatment unit upstream of an underground detention system and then through an end-of-pipe water quality treatment device before leaving the site. If we utilize rainwater harvesting on the site, we could decrease the size of the detention system. As you can see from the graphic, the rooftop runoff going to a rainwater harvesting system gives the opportunity of shrinking down the size of the underground detention system. That will save some space, that will save some costs. And again, the surface runoff with the parking and the green space going into the detention and then out through a water quality device, the rooftop draining into the underground pretreatment cistern and then getting pumped to be used for irrigation. The surface runoff treatment and detention systems consisting of an underground CMP detention system in through a water quality device typical of a Contech storm filter media cartridge media filter type unit, and the roof runoff going through the CDS, the underground cistern, and the mechanical system. So let's look at costs. On the left you can see the pond cost from example 2. On the right, the underground detention system with an estimated materials cost of $80,000 and an estimated installation cost of $115,000. The added cost of doing that instead of the pond is the difference, which is $85,000. If we also incorporate rainwater harvesting with that design, the detention system is slightly smaller, but we add in the rainwater harvesting system, and the incremental cost to incorporate that design is $164,000. So what would the $164,000 additional cost represent for benefits down the road if you incorporate rainwater harvesting? As discussed before, there's the water savings from using that water. The irrigation only estimated at $1,200 per year. And if you are able to use it for more uses, like irrigation and toilet flushing, that could be as much as $6,500 per year. With putting the stormwater detention system under the ground instead of the above ground pond, you gain room in your parking area for additional parking spaces. Those additional parking spaces allow you to put a larger building in place, for example, and the additional square footage of that additional building space would net an estimated $1.6 million opportunity cost available to the developer. And again, we have the rainwater harvesting lead points that are available up to 12. Let's jump out to a participant poll. Does the area that you work in or design your projects in have any monetary incentives for water reuse, such as tax breaks, stormwater fee credits, or rebates? If you can go ahead and click on your screen, yes or no, if the areas that your projects are mostly involved in have any opportunity to for incentives for water reuse, such as a tax break, stormwater fee credit, or rebates. Go ahead and click on the screen, and we'll put those results together as soon as we get enough people to answer the question. Great. We have the results in, and it looks like the majority of people do not have an opportunity for any incentives for water reuse with a tax break, any kind of stormwater fee credit, or rebates. That's unfortunate, but I think as we move through modern times and the LID movement is gaining traction, I think we'll see more and more opportunities for those types of rebates. Well, we've had some questions come in from the audience. One question is, do you need to pre-treat the roof water? Catherine, would you like to take that question?
Sure. So we do recommend pre-treatment no matter what the surface you're collecting off of is, if that's roof water or hardscape water. Even with roof water, you're likely to still get organic materials such as leaves or pine needles floating off the roof. There's also animals, birds and such that can cause items to come off the roof, and then atmospheric deposition as well. So all of those items, it makes it much easier to have a pretreatment system to maintain upstream than having issues potentially downstream with your fixtures or increasing the maintenance burden on your cistern. So we do recommend, even for roofs, to have a pretreatment upstream.
Great. Thanks, Catherine. Also, another question came in, how does rainwater harvesting work during the winter? Do you divert the runoff during the winter weather? Well, it depends if you're in a freeze-prone area or not. Winter collection of harvested rainwater works similarly. If it's on top of the building heat generally will melt the snow on top of the building, so you will still get runoff into the cistern even in a very freeze-prone area. If you want to use that water for winter use, like a processed water, a washdown area to your maintenance equipment, if you're in a town, for example, or toilet flushing, you can reuse that water during the winter months, and you would have to capture some of that water to be able to use that water during the winter. Typically, the mechanical system would be indoors or in a heated room at that point, so that the freeze-prone areas do not affect freezing out the pipes, etc. So with that, let's continue on with the presentation. What if we could utilize the detention with the rainwater harvesting system? If there was a way to use that existing detention system without having to put in the more expensive watertight cistern that is typically seen with most rainwater harvesting systems. It's a very good question. With that type of application of the technology, there are some challenges that come with that. Some of those challenges, and we'll circle back later and answer, provide explanation to the challenges, but detention systems are designed to slowly discharge over time. That's a basic stormwater design. The tank empties out over time, so it's available for the next storm event. Well, does that leave enough water to harvest and reuse that water? That's a very good question. Second challenge, detention systems are not typically designed for zero leakage. They will leak over time. It's a stormwater system that's kind of in their design to do so, and it's okay for them to do so, but will that detention system leak out and be empty when I need the water? Well, that's a possibility, but we can take a look at that. That is a challenge that needs to be considered. And how much will it leak? And another issue is that if you take the entire surface area and run that into the detention system and try to use that water from the entire site, including the parking area, will that have a potentially higher pollutant load that you're introducing to your cistern, and therefore pumping that up to your mechanical system? Will that have an effect on either the health and maintenance issues of the cistern and the mechanical system? We will definitely circle back and discuss those challenges after we get through the next section. And so I will turn it over to Matt Ray to discuss the OptiRTC.
Thanks, Dave, and I'd like to thank Contech for having me today so that I can present this new exciting technology to everybody on the call. And it's what we believe is the future of water infrastructure management, not just from a rainwater harvesting perspective, but from a municipal, CSO, and any type of controllable system that Opti can be implemented on. So we'll be talking about harvesting in the example today of using that underground CMP detention system for reuse without putting in a separate cistern. So before we start talking about how that's going to work, let's introduce the platform as to what is OptiRTC. So Opti is a cloud-native platform. It uses sensor data, forecast information, and modeling to actively control water infrastructure. So let's go through each one of those points there to dial this down as to what exactly it is. So Opti, being cloud-native means that when you install Opti on a project, you get a login to the Opti website where all of your data lives on the cloud, so you can access it from your phone, you can access it from a computer, anything that has an internet connection. And so all of your decision-making processes happen in the cloud. You can control your system from any device. And so the way it works is that Opti takes sensor data that you've installed in your system. So our CMP detention system will have a level sensor. And what it will do is it will incorporate that data. It'll take forecast information. We use NOAA, the government forecast service. And all of these things are continuous. There's no like every 15 minutes or anything like that. It's a continuous read of sensor data forecast information. And then what it does is it uses very complex algorithms to determine the amount of rain that's going to come into the system based on the forecast probability of precipitation and the level in the tank to maximize the storage of your tank, to maximize the capture of that rainfall so that you have very little wet weather flow, if any. So how does this fit into the Contech, stormwater staircase that we talked about earlier? And so what Opti does is it provides a bridge between a detention storage system and a runoff reduction system, with the goal being that with active intelligence, you can reduce your runoff potentially by a multiple of 2 or 3, and we'll go through those numbers later. So let me give you a little flow chart here so you can actually visualize how Opti works. So Opti is just the platform that's in the cloud. In the field, you have your CMP detention system, you have your level sensor, and you need to install a valve at the exit of that detention system with an actuator. And this usually involves a slightly upgraded mechanical panel that Mark talked about. So we'll have the Opti system in that panel so that it can use that actuator to open that valve when it determines that it needs to drain that system. So it takes continuous readings from the level sensor valve and mechanical panel, brings in the NOAA forecast data, runs through the calculations, and makes the decisions for the system. The thing on the right there is the dashboard that we'll drill down into. That's really just a representation of what it does for the end user. And so whenever you install an Opti system, you get your login, you log into the cloud, and this is what you'll see when you first go in. And this is a user that has multiple systems. So each one of these squares is a system that you can then drill down into. The bottom right is regional users. If you want to use a map view and see all of your systems as they're laid out, you can zoom in on those and see where you have all your systems installed. So what this is an actual project, the EPA headquarters. This is in the basement of the EPA headquarters, and what you see here is when you drill down into one of those squares for your project, this is an actual 3D rendering of the live storage in those tanks that they have in their basement. And so what you see on the left-hand side of the picture there is the operations panel, where when it's clicked on automatic, Opti runs the system. But there are levels of control here where the end user can open their valves, they can drain the tanks for maintenance, if for any number of reasons that they want manual control, that's there. And then from this same area, the user can set up alerts that they want. so that if your tank goes below a certain level, you can get a text message or an email or a phone call. If there's a probability of precipitation over a certain extent, it's really limitless as to what level of information you want to be provided to you. That can be automatically generated by the cloud and by Opti. And so here's the technical details of the breakdown of how Opti actually operates. And what we'll look at is the top two graphs right now. The top right graph is the precipitation forecast for this particular, for the EPA region, for the headquarters. And what you'll see is that, oops, sorry about that. What you'll see is that the dashed red line on the top right of that slide is the probability of precipitation that EPA has set that they want the algorithms to use as their checkpoint, really, for when they want the tank to empty. So depending on the size of your cistern, the risk of CSO overflow, the credits that you get, you can change the probability of precipitation where you want the system to act. So in this example, it's set at, I believe it's 55%. They range from 50% to 70%. So what that means is when the forecast data comes in that says, okay, we've got a 70% chance that we're going to get an inch of rain in the next, like 12 hours from now. What that'll do is that Opti will do a mathematical model, figure out how much volume is in the tank, how much rainfall will fall on the site, given that probability of precipitation, and then it will start, figure out when to start to drain the tank so that the maximum volume of the storm is available in the tank when it's going to occur. So that essentially that storm creates zero discharge from your site. So that, in those of you that are in CSO markets and understand that will understand the importance of that, being that by being able to drain these tanks before the rain events, you can effectively eliminate this combined sewer overflows from a municipality. And so what the graph on the left shows is the green is the tank's storage volume that's available. The red is the forecasted precipitation volume. And then the algorithm tries to match the slope of the discharge line to maximize the capture values. So what are the benefits of putting an Opti on a rainwater harvesting system? So the first obvious one is capital cost savings of using a much less expensive CMP detention system type of basin instead of a fiberglass or a steel reinforced polyethylene pipe system, which is progressively more expensive than the CMP. And so what you can do is you can rainwater harvest from this one single detention tank. And what you can do is you can decrease your return on investment time by a factor of 3 to 4, and that depends on a lot of factors, whether that's 2, 3, 4. Depends on the water and sewer rates in your area, what the installed tank size is going to be of your cistern, and whether or not having an additional volume for harvesting can add an additional use benefit that you didn't see possible, such as, maybe the space was limited for your cistern, so you were just going to do irrigation, but now you can do toilet flushing because you have all this volume available. So what you can do is you can, usually a detention versus a harvesting volume could be a factor of 3 versus detention versus reuse. And so what you can do is you can increase that availability of rainwater harvesting by a factor of 3. And while not as important on just pure rainwater harvesting projects, you get a dramatic increase in wet weather performance. And we have many projects installed in the field where we see between 70 all the way up to 95, 97% reduction in wet weather discharge from a system using OptiRTC. And then again, you get the lead points and everything else that we talked about before. So what additional things do you need on your site so that you can incorporate Opti into your system? Well, like we said before, you need to have level control, you need to have valves and actuators, and then you need to have internet connectivity at your mechanical skid. It can be wired, it can be wireless, it can be cellular. solar powered. There's numerous ways to do this, and internet connectivity these days is not a huge hurdle with Wi-Fi and everything all around us at all times. We have to look at regulatory considerations. We'll talk on the bottom one first. So water rights. So before you start designing a system with Opti and before you use one tank for harvesting, you have to ask yourself, are we allowed to harvest the water from the surface for reuse in a building? Certain municipalities, certain states, certain areas do not allow you to capture water from the ground. So you have to ask that question first. And then on the positive side of the regulatory considerations is with OptiRTC, you have continuous monitoring of your site, of your performance. That's completely verifiable, completely auditable if you're in a compliance situation, or if you have, if you're doing a pilot study or a study program or any kind of, where you need results. And these live on the cloud, accessible from anywhere, and for a extended period of time, this data would be available for you. And then I got a question I get a lot of questions before about fail-safes and security of the system. So the way Opti is designed when we use it for this use for a detention basin is harvesting. So the detention basin will still be designed with an orifice outlet to meet peak flow requirements, things like that, with the valve and the actuator on it, so that if Opti loses power, if internet connectivity goes down, if anything happens to the system, it automatically reverts to a standard detention system with that peak flow orifice or whatever orifices that need to be designed for that system, and until you can get out and fix the problem. And anytime that any kind of catastrophic problem would happen, you get immediate alerts to go and correct that problem. And then finally, the security of the cloud. How secure is my data? Can somebody hack my storage tank and drain it? And so Opti has multiple levels of development where they think about this kind of thing every day. And we're on the Microsoft Azure platform, which is the only cloud platform that has gone through the FedRAMP process to be allowable to use on federal sites to store federal data. So it's the highest level of security you can get in the cloud platforms, higher than banking software that people log in and look at their account information on. So I'd say the risk is pretty minimal for an end user from that standpoint. And then just finally, I want to say that on the non-rainwater harvesting side, that there's a tremendous benefit in CSO credits. That if anybody's in a CSO market, OptiRTC is that wet weather performance is a huge deal right now on a lot of East Coast markets. So feel free to contact me with any questions through Contech through this presentation. I'd be more than happy to walk through any of these items that people need more details on. And with that, I'll turn it back over to Mark.
Great. Thank you, Matt. So this is yet another configuration of integrating rainwater harvesting into your stormwater management plan. So as you can see in this configuration, OptiRTC is controlling the outlet valve on the detention system, as shown here. And then we can reuse the water stored within that detention system for irrigation or toilet flushing or whatever our reuse application is. So as we previously discussed, the CMP detention system will experience some leakage. So here we've assumed 2,000 gallons per day, or about 2% of the total volume. So let's take a look at how that affects water availability. So what we've done here is we've used our runoff reduction calculator to run a simulation using 20 years of rainfall data to see how a leak of 2,000 gallons per day affects the water level in the system. So the top graph represents the 31,500 gallon SRPE cistern. You can see there that in this scenario there's no leakage of that tank. And then the bottom graph shows the water level, which does take into account the leakage of the 105,000-gallon CMP detention system. And so you can see that the leakage really has little effect on water availability, and the detention system actually goes dry less often, and the water availability actually increases by such a large detention system. So let's circle back to our challenges. How do we overcome those challenges? Okay, the detention systems are designed to slowly discharge over time. So by using OptiRTC, we're able to hold the water in the detention system, and we only release it to make room for predicted rainfall amounts. So we do this instead of slowly discharging it over time so that we have the maximum water availability possible. And so in the previous slide, we've addressed the leakage issue. We've demonstrated that the volume of water stored in the detention system is so large that the small amount of leakage does not affect the water availability. So, and this is something that's going to change from one site to the next, and this is something that can be simulated for different size systems in different rainfall distribution patterns by using something like the runoff reduction calculator. So as far as the surface water quality, to address the higher pollutant loading of the surface water, additional pretreatment or some type of enhanced filtration will be needed, and depending on the reuse application. So depending on the types of pollutants, oil and grease from a runoff, from a parking lot runoff, and depending on what the reuse application is going to dictate how complex that pretreatment needs to be. So as we wrap up, we've presented a number of different project examples using various assumptions. The important thing to realize is that every project will have a cost to comply with the stormwater management rules. So as we've demonstrated, integrating rainwater harvesting as a part of the stormwater management plan will impact the overall cost of stormwater management. So we're going to add some costs, but we're also going to decrease the treatment area and the cost of other stormwater management practices. So when we are evaluating the cost of rainwater harvesting and weighing that cost against the benefits, such as opportunity costs, water savings, lead points, as we're doing that, it is the incremental cost of adding rainwater harvesting to stormwater management that must be considered, and not just the capital cost for the rainwater harvesting system itself. So this concludes our rainwater harvesting webinar. Thank you for joining us today, and I think we may have some questions and some closing items. Lisa?
Thanks, Mark. Catherine, did you want to take care of the questions?
Yeah, let's take a couple questions. We've received a lot of questions today, so we will go through a few of those right now, and then if you didn't hear an answer to your question, we will follow that up with an email later. So let's start with, Dave, what kind of maintenance is required for a CDS unit, and how is that maintenance typically performed?
Thanks, Catherine. CDS pretreatment units are a manhole-based unit, typically to clean out that kind of hydrodynamic separator type unit. A Vector truck would be dispatched to the site and the system would be vacuumed out. With any kind of stormwater management maintenance program, inspection is a critical part of that to know when that is necessary. So basically you would pop the manhole top and visually inspect the unit, maybe take a sludge judge and measure the sediment pile at the bottom or the oil sheen at the top, and that would dictate when the system would require maintenance. Maintenance costs on those would typically be anywhere between $600 and $1,200, maybe up to $2,500, depending on local budgetary numbers from vacuum truck companies. And typically, it depends on the influent concentrations of the pollutants, but which would range the cycle time of how often it would need to be done. But anywhere between 6 months for a really dirty site, every 2 years for a cleaner site, that kind of outlook.
Great, thank you. I'll take a question about regulatory requirements. We had a question, what are the typical regulatory requirements that exist for what harvesting rainwater may be used for? And that really does vary across the country. Most places allow you to use it for irrigation. Sometimes with spray irrigation, you need to use a disinfection system. And then if you're bringing the water inside the building, for toilet flushing, often additional disinfection will be required. Excuse me, sorry. Let's see, how about, Mark, how does the parking spaces equal an increase in rental space?
Well, if you look at the, most jurisdictions will require a certain number of parking spaces per, say, 1,000 feet of building space. And so in the assumptions that we used, I think we used a 1.5 parking spaces per 1,000 square feet of building space. And so in many areas that number can be as high as 2.6. So that was used in the equation to come up with an opportunity cost for rental space.
Great. Let's see. And then, Matt, we have a question about OptiRTC. Is the Opti software actually learning and adjusting based on each system, or does it use static algorithms?
Currently, the systems use static algorithms based on set points that the user enters. But currently, the next iteration of Opti will be learning algorithms. That's probably a year in advance from right now.
Great, thank you. Let's see, Dave, how watertight is watertight for our steel reinforced polyethylene cisterns? Does it have like an allowable leakage rate associated with it?
With any kind of watertight system, you probably want to specify a certain amount of water tightness. There are different levels of water tightness and different definitions of water tightness depending on what perspective you're coming from. There are some ASTM test specifications for watertight testing of systems after being installed. We typically recommend a hydrostatic test, which is to install the tank and make sure the connections are made and backfill, and before turning over to the owner, the installing contractor may have to do a hydrostatic test, which is basically fill up the tank, let the tank relax, and then measure the height of that water, and then come back in a certain amount of time, 12, 24 hours, whatever length of time that is, and then measure that height again, and that would give you your overall leakage rate for the tank volume in a percentage.
Okay, great. I'll take a question about using reused water. Question was, have you ever combined runoff with reused water that would allow the system to fill with treated wastewater effluent during a dry period? And that does come up. We have projects where they're only able to store a limited amount of rainwater in a drier climate, and then instead of using municipal potable water as your backup water source, they're able to take, highly treated wastewater effluent, reused water, and use that in place of the potable water. So basically eliminating any potable water usage for whatever your end use of your rainwater harvesting system is. That can also be a great benefit for LEED projects, to be able to say, I'm not using any potable water for, say, my landscape irrigation. So that is an option, and we can work with you for different makeup water sources if that's something you're interested in. Let's see here. How about, actually, I'll take one more question about, we had a question about collecting water off an artificial sports field, and we have seen that in some projects. One thing to be aware of is those artificial sports fields often give off little rubberized pellets, so we want to make sure we design the pretreatment system to handle that type of loading from the site, and then make sure that it is designed for the flow rates coming off of that artificial sports field and any other sediment. So we can do that, and if that's something that you're interested in, we can help you out with that type of project. So let's see if we have one more question we can take. Mark, approximately how much cost do you need to add if you're upgrading your mechanical system from just using it for irrigation to using it for toilet flushing? Mark's not available. Is Dave available?
Yeah, I'm here, Catherine. Sorry.
Okay.
Yeah, that's an excellent question. Yeah, our typical irrigation system is usually a manual flush filter, and there's usually no need for UV disinfection. When we upgrade the system, we're typically talking about a finer level of filtration, which can sometimes increase the size of the filter. We're looking at typically automatic back flushable filters, and then also the addition of UV. And what we've seen from an irrigation, a standard irrigation type mechanical system to toilet flushing will roughly double the size or double the cost of the system. So if we're talking about a $20,000 irrigation system, to upgrade will typically cost about $40,000. I think that's a good conservative estimate.
Great. Well, I will turn it over to Lisa.
Thank you, Catherine. Ladies and gentlemen, there have been a few questions come up regarding the PDH certificates. At the close of the presentation, a new browser window should pop up on your screen with a survey about today's webinar. After you submit the survey, your responses will be manually processed, and you should receive a thank you for attending email within 24 hours with a link to download your PDH credit. Also available in this email will be a PDF copy of the presentation. Again, this process is manual, so it will not be available immediately following the presentations. If you have any other questions or if you have not received your email within 24 hours, please contact info@contactes.com. And as Catherine stated earlier, we will be following up with an email about the questions that were asked during the webinar. There were many, many good questions that we did not get to, and so we'd like to put together a frequently asked question list and get that out to everyone who participated today. Again, we thank you for your time and hope you learned something from our webinar, and have a great rest of your day.